Hello, folks. Welcome back. Seems like it's been forever since we met, right? But it's only been a week. That seems like forever, though, huh? It's fall. Did you notice? Amazing. I know, right? So I'm on my laptop today, which means that I will be less angry as the computer refuses to let me do something. It also means that our course is live streaming right now. So how cool is that? I'm on the YouTube. So I've disabled comments, but if you're ever away from class and would like to watch it during this time, you can. Otherwise, I'm going to post the videos after the fact, just like usual, except that they will direct you to the YouTube rather than wherever they are buried right now within the bowels of the KU system. So we'll see how this works. So over the long weekend, I was pleased to see so many of you busily working on making friends with SAS. Answered a lot of questions. One question that I think I've answered, pretty much every single person has asked me this at one point. The idea of making a second indicator of time. So you'll note in the beginning of homework 1's description, there's this sentence here that says time 2 was collected after 3 months, time 3 at 12 months, and time 4 at 24 months. So the idea is that even though this is a longitudinal study in which I asked you to indicate which wave of measurement it was with a variable called occasion, that goes 1, 2, 3, 4. We can't use occasion as a predictor for time in the model because the distance between occasions is not equal. When we interpret a slope of change per unit time, a unit has to mean something. And if one unit is 3 months and another unit is 12 months, then a slope for that variable won't make any sense. So even though it might seem redundant to have 2 different variables for time, you actually will need both because they get used in 2 different places in the code. The variable for occasion that I asked you to make when we were stacking the variables here is going to be treated as an ID variable. It's going to help keep track of which row is which in terms of the program syntax. The second index, which I'm calling year, so note that you need to convert months to years, then is going to be used as a predictor in the model that keeps track of exact time in study. There are 2 ways to do this. Number 1, the way that is easier but potentially less generalizable is after you stack the data to make a second data step in which you recode, occasion into years. So it would look something like data, name, set, name, and then if occasion is 1, year is 0. If occasion is 2, year is 0.25, and so on. That way works just fine if everybody is measured at the exact same occasions. You have balanced data. If people are measured at different times, then the other way to do this would be to create variables in your data set that keep track of exactly when occasion 1 was for each person, when occasion 2 was, when occasion 3 was, when occasion 4 was. You would then feed those 4 variables into the stacking sequence and stack them just as you did the DVs for that each occasion. So the latter is the way that I would recommend if you're going to be working with unbalanced data, because it works better for that case. Another question I had was about this idea of saving your output as an Excel file. That file won't open in SAS, it will open in Excel. However, when you go to open it in Excel, you'll get an error message saying, hey, are you sure you want to open this? It's not really an Excel file, right? That's because it's an HTML file. Shh. Just say, yeah, it's fine. Hit OK, and then you'll be able to open it. So the purpose of this step is so that no matter whether you're on a computer that has SAS or not, you can save the results of your analysis for viewing later. You can also send this to somebody who doesn't have SAS or doesn't know what SAS is, because everyone has Excel, whether they like it or not, or whatever the Mac analog is, right? What is it called in Mac? Like Mac Office or whatever? No? What is it called? No, it's not a thing?
No, I have no clue.
Okay, but you have an Excel-like thing, right?
I've never used it. Oh, numbers? It has all numbers or something.
Does it open XLS files? There you go. So yes, the idea is to take these program-specific files and to save them in formats that anyone can read, including you, if you don't have SAS on a computer. So that's the point. Any other questions about this assignment while we're on topic? Okay, if you're still having problems getting this SAS to work or getting this assignment done, please let me know. Otherwise, it is due on Friday via Blackboard. The remainder of the semester, all of the homeworks are going to be available in the homework portal. So let me make sure you all know where that was. If you go to our courses website, there's a link to it up here at the top. You would sign in using your own information. And then you should have both 0 and 2 available to you. I'll go ahead and click on 2 so you can see what it is. Homework 2 should not take you very long at all. That's it. It's one real model, and it's a regression model. You don't even need mix to do this, but the idea is to get you used to looking at mixed output and interacting with the syntax before we start adding the complexity of new models. And so that's what we're talking about today. And this is the homework that is due that goes with it. This is not due until the 15th though, so a week from Friday. All right. Yes, here's the YouTube lags a few minutes, but it should be live streaming here. So if not, then oh well. I'll have to figure it out later. All right. I don't need Excel right now. I don't need this. I do need this. So this is where we left off last time, a reintroduction to general linear models. Since it's been a week, I'll go ahead and hit a little bit of review. The big picture in terms of general linear models is that when people use these words, ANOVA, regression, ANCOVA, MANCOVA, MANOVA, what they are talking about are two things specifically. Models in which your residuals are supposed to be normal, so not the outcome, but the outcome after controlling for model predictors are supposed to be normal. They're supposed to be independent. And these models are typically estimated using least squares because you can calculate it by hand. Least squares is something that was developed in, I think, the 1800s. It always works if you have data that lend itself to that. But very quickly we'll find ourselves in situations where that is not the case, which is why I am teaching you the same ideas represented in a maximum likelihood-based framework. So this is where we left off. This class, I think, and maybe in the next one, we'll see how long this takes. We're starting with models you know, general linear models. I want to show you what they look like in mixed. We're going to do main effects now, main effects of continuous predictors and categorical. We'll pick up interaction terms later in the semester when they get relevant. But what is new is that we're going to learn how the same concepts that you learned in terms of least squares are the same or different in terms of the code and the output when you're using restricted maximum likelihood. So we're starting on slide 15. I will refuel. Any questions before we dive back in? All right, you ready? You pumped? I have a new handy dandy remote too I found in here. Tell me what you want to do. Oh, there we go. So yes, two sides of any model. You will hear me say this over and over and over again. Here's your first instance of that. Model for the means versus model for the variance. When I say model for the means, I mean the fixed effects. That means effects that are constant for everybody. Like everybody gets the same intercept, everybody gets the same effect of x, everybody gets the same effect of z, and these variables are always part of your data set. So they are fixed effects of known pieces of information, things you have measured. Each fixed effect is going to be characterized by 4 or 5 pieces of output. So these are things that you've seen before, but I want to pay attention to what these headings are called because this will be common across programs. The estimate itself, that's the column you're used to looking at for the coefficients. It's standard error. Smaller is better. So smaller standard errors are found when you have larger samples or less residual variability. It's an index of how certain the algorithm is that this really is the best estimate for that parameter. A t-value or a z-value you will see one or the other in your output, and I'll talk about the difference in just a second, and then a p-value that goes with this, which is the probability under a null hypothesis of observing that fixed effect if the true fixed effect is 0. You can also ask for confidence intervals, and so the confidence interval conveys the certainty, the range in which that parameter is expected to be 95% of the time. This process, this run your model, look at the coefficient, stare at the p-value that comes with it, that is formally called a univariate wall test. Whether or not this wall test is based on t or z differs by program. So here is what it means when you see a t versus a z, and here is where you'll get it. So a univariate wall test, when you are testing one fixed effect, you're testing one intercept or one slope. That slope can be for a main effect or it can be for an interaction, but the idea is that it's one fixed effect. If you are assuming that your denominator degrees of freedom for that effect is infinite, that is what a proper wall test is referred to, then you'll see a z. So in M+, for instance, that's what they do. In Stata, that's what they do up until version 14. I have a few Stata people in the house, right? You, sir, and you, yes. Raise your hands. Stata's a lovely program. Yeah. So Stata folks, starting in 14, they offer you choices as to whether or not you want to use degrees of freedom. Prior to 14, they did not. So Stata defaults to a proper wall test in which you don't have to worry about denominator degrees of freedom. Otherwise, if you do have denominator degrees of freedom, it shows up as a t. If you have a test of more than one effect at the same time, the idea that multiple fixed effects as a set make the model better, that is called a multivariate wall test. And the analog to z is chi-square. The analog to t is f. So if you're in a program that uses denominator degrees of freedom, you'll get t's and f's. If you're in a program that doesn't, you'll get z's and chi-squares. Which set you report is up to you, because f times degrees of freedom is chi-square, as I recall, or I might have it backwards. They're linear combinations of each other. So in proc mix, you get t's and f's by default. You can also ask for chi-squares for that as well. There are various options for denominator degrees of freedom. I pretty much am going to leave this alone across class and use Satterthwaite, which is the most general. These are talked about in chapter 5 of my book, and it won't be relevant until we get into longitudinal data. But the idea is that you're paying attention to how many actual cases you have as opposed to assuming that you have an infinite population. In practical terms, once you get past like an n of 20 or so, these things really don't matter and you'll come to the same result. So standard errors, where do these things come from? Here is a formal representation of that. A standard error is like a standard deviation for the sampling distribution of that parameter. On the numerator of it is the residual variance of y. So basically how much variation is left over. On the bottom, the denominator, is variance of the predictor. So standard errors are scaled, reflecting the predictor that they are the standard error for. And the sample size. When you have more than one predictor in the model, it changes to include the unique variance of the predictor and the R square here. So this term right here ends up becoming how much variance does the predictor have that the other predictors don't. So what this means is that standard errors are higher for the same predictor if there are collinear predictors in the model. That's the collinearity problem you've all been warned about. It's not really a problem other than it gets harder and harder to show unique effects if the effects that you're looking at are from correlated variables. But the other piece of that is because residual variance of y is in the numerator, a predictor that was not initially significant, when put in a model that is better, that has a smaller residual variance, it can become significant. So that's something to watch for when you're doing analyses. If you're deciding whether or not to keep something, that answer could actually change depending on what's in your model at that point. So if the standard error is smaller, that means your t ratio of the estimate over the standard error is bigger, and that means your p-value is smaller. Okay, so you've heard most of that before, right? That should not be new information, maybe some new words, but same concepts. Now here is a concept that you may not have heard before, but you have heard it, specific instantiations of it. Multivariate wall tests. Now this is something that is talked about in the context of multi-level models, and for many years I had no idea what these things were. I was like, I don't understand what you're talking about here. And then a couple of years ago, I finally was able to put it together what this actually is. You already know how to do this. You just don't know that you know how to do this. So if you run a regression model, how do you know that your R-square is significant? What shows up on your output to tell you about that? Not a trick, I swear. Sir, in the back.
Its value relative to the null model.
So you get an R-square value. How do you know if that is significantly greater than 0?
It's modeled as F. The ratio is modeled as F distribution.
Yes, F. You get an F test for it. That F test is a multivariate wall test. It's a test of whether the set of fixed effects you put in the model as a whole account for significant variance. Do you remember hierarchical regression or stepwise regression, where you put in some stuff and then you put in another layer of stuff? You can ask your program for a change in R-square F test as well, right? That's a multivariate wall test. If I do an ANOVA, let's say that I have 4 groups, I get a main effective group F test, right? If I have 4 groups, how many degrees of freedom would that omnibus main effective group have? And don't say 4. If I have 4 groups, if I'm testing the significance of group, how many degrees of freedom is that test? I know you know this, it's not a trick, I swear. Don't say 4 and don't say 2. There we go, yes, if I have 4 groups, and I do an ANOVA, I get an omnibus main effective group F test that should have 3 degrees of freedom to it. Is there any overall difference across these groups? That is a multivariate wall test. So those things are spit out by convenience. If you do an ANOVA, you get that omnibus effective group and interaction terms. If you do a regression, you get that F test for an R-square. You have to ask for that stuff in proc mixed, but it's the exact same concept. And you can get it for any combination of model parameters, not just the ones that show up by default. So what the code is going to look like then to do that, here's our most basic form of proc mixed. So mixed means models with fixed and random effects. Since it can do both fixed and random, it can do just fixed, which means you can use proc mixed for t-tests, ANOVAs, regressions, ANCOVAs, what have you. This last part right here, method equals REML. Do you remember what REML stands for? I'll give you a hint. The last word is likelihood. What's M? Maximum. What's the re part? I'll accept 2 correct answers, depending on whose book you're in. Restricted is 1, residual is the other. Now don't let the name fool you. It's not really restricted in any like it's bad sense. It's actually better than regular flavor maximum likelihood when it comes to recovering model parameters in small samples. For your information, restricted maximum likelihood is exactly the same thing as least squares if you have complete data. So the results that you will get out of this are exactly what you would get if you ran a regression or an ANOVA using least squares. I'm showing you what it looks like in mixed so that we can then generalize what it looks like once you add other types of effects you're not familiar with yet, random effects. So like every other proc in SAS, you have to say, where would you like me to apply this analysis? Data equals, work is where the data set is, and then the name of the data set. Note the equals goes here when you're just referring to a data set to do manipulations to it. There's no equals, but because this is an option, I do have an equals here. It details just asks for an additional printout that will be useful later on. Now this statement here on model, this is the big one. This is where you tell it what your model is going to have in it, and it looks like an equation. The outcome variable goes first, equals, and then whatever fixed effects of predictors you want. So here, I'm asking for x1 and x2. By default, these predictors are treated as continuous variables. There will be an additional statement required if they are not continuous variables, if they are grouping variables instead. Anything after a slash is some kind of option. Solution means, hey, can you actually give me the results? That's not a default. I know, right? You have to ask for the results. That's not a default. These are the same people who put the run button next to the delete key. Yes, sir. What is your name, sir, by the way?
Charlie.
Charlie, okay.
So does it just give you the coefficients if you don't put solution?
It gives you type 3 tests of fixed effects, but it does not give you any coefficients if you don't put solution. If you do, you get the coefficients, the estimates, standard errors, and the wall test for all the coefficients in the model. So if I wanted to get a test then of whether or not these two predictors gave me a significant R-square, a significant reduction in variance, it would be accomplished via this third line here, contrast. That's a SAS statement. In pink are words that you put. You can write anything you want. It will show up on the output as a label, which is really nice because then you can write what it means and you don't have to remember what it means later on. We separate degrees of freedom with commas here, and what I'm asking for is 1 coefficient of x1 and 1 coefficient of x2. Later on, you'll see sometimes -1s and 1s. That actually refers to differences in coefficients rather than both together. But this is going to spit out an F-test for whether or not those two coefficients together make a significant model, make a significant reduction in variance. You'll get a chance to practice this on homework 2. With me so far? Not new stuff, right? Just maybe a few new words here and there? Good. So when we put in effects of predictors, everything must be centered forever and ever, amen. All predictors must be centered from now on. This only matters sometimes, but it's a general practice that is always useful to do. So we're talking about how to specify the model for the means. Why isn't this usually a thing? Because whether or not you center a predictor, whether or not it has a meaningful zero value is what I'm talking about, it does not affect the R-square. And if we have the same, let me see how to say this right here. It does not affect the predicted values, let's put it that way, as long as you have the same model. So why do we care? Because the intercept is predicated on centering the variables. The intercept is always going to be the expected y when all the x's are 0. So the only way to get a meaningful intercept is to have meaningfully scaled predictors where 0 means something. Now what it means is entirely up to you. There's no wrong choices, there's just weird choices. This is going to matter more once we include interaction terms, because the main effects are going to be specifically when their interacting variables are at 0, as well as when we include random effects, which are variances around these effects. If the fixed effect itself is meaningless, it's going to be way harder to find a variance around it. So let me put it to you this way. Why the intercept should be meaningful. So this is a map of Concourse B at an airport. Any frequent flyers want to tell me where this is? It's a popular connecting destination from Kansas City. Anytime you're heading east. This is Atlanta. Yes, this is Concourse B. So if I'm going to Atlanta and I know that I have an hour to get dinner before my connecting flight, I'm headed to Concourse B. I'm looking for the Manchu Wok. Airport Chinese food is usually my go-to. But what's the first thing that I have to know before I can figure out how to get to the Manchu Wok? Where I am, right? The first thing you need to know when you stare at any map is the "you are here" sign, because everything is relative to that. The same is true in data analysis. the intercept is like the "you are here" sign. The way that we talk about slopes is as x increases or as x decreases, but relative to what? If the intercept is in the middle of the data, for instance, if I centered math at 50, then my intercept, the "you are here" sign, would be right here, and I could talk about what happens as math goes up or math goes down. In contrast, if I centered math at the lowest score, let's say that looks to be about maybe 30 in this data set, it only really makes sense to talk about what happens as math increases because I don't have anybody for which math decreases. So the intercept is the "you are here" sign of the model. Everything is scaled relative to it. So it is very helpful in interpreting model results to have a meaningful intercept, one that is within the scale of the data. That being said, if you want to look at multiple intercepts, you are allowed to do that without having to rerun the model with differently coded variables. That is where we have a new friend, another piece of code called estimate in SAS. The good news is that every other program has the same type of code too that allows you to request model predicted combinations of fixed effects. So in SPSS mixed, it's called test. In Stata, it's called lincom. And it's also accomplished via new and model constraint in M+. It is how you ask the model to generate predictions for what would happen if the intercept was someplace else. So I'm going to teach you these because I really, really wished I knew them earlier. They are super, super useful and we're going to use them a whole lot. So here are some basic rules for asking for estimate type statements. If we're using them to generate a predicted outcome, so a predicted intercept at some other point in the data, you have to refer to the intercept. Otherwise, you're going to be referring to the predictor variables. The default, if you don't mention a variable, is it's 0. And if it's a categorical variable, which we haven't talked about yet, that default varies by program. So centering, this is the idea here for centering. We're subtracting or adding some constant so that 0 is within the observed scale of the data. Now, most of the time, you'll hear this with a phrase in front of it, grand mean centering. Have you heard that phrase? That just means you pick the grand mean of the sample. That's fine. However, that may not be as useful as another one. So for instance, if I have a variable measured in adults that's something like years of education, the average years of education in my sample might be something like 14.67 years. Now I could make that the centering point for education, and I could talk about someone with the average level of education as my reference point. But do you think there's anybody in the sample who actually wrote down 14.67 years? No. Now furthermore, if I were doing an analysis, say, of university community older adults, which always means ex-faculty members and their spouses, average years of education could be like 21 years, right? Those are very different types of samples, and so just saying this is someone of average years isn't that informative if you're looking to compare across studies. What I would do in that case instead is, in the first case, I might say, all right, my reference point for education is 12 years. My average person that I'm going to refer to as my "you are here" sign is a high school graduate. Then I talk about what happens as I move up or down the scale relative to that kind of person. In the other sample, I might pick, let's see, what's a master's degree? I gotta do the math here. Bachelor's would be 16-ish, 17 years, 20-ish, we call that master's degree. You guys are thinking now, I'm in what, 28th grade, I think, something like that? Yeah. It's kind of depressing when you put it that way. But, point being, that might be my average person in that group. But tying it to an actual person who gave you a value in the study is probably going to be more useful than the grand mean, unless you're dealing with a variable that no one understands the scale of, in which case the grand mean is just fine. So these types of estimate statements can be used to generate model predicted values. This is the kind of thing that you can do easily in Excel as well. The advantage to doing it in here is that not only do you get a model predicted value for whatever combination of predictors that you put in here, but you also get the standard error that goes with it. So then you can calculate error bands around your sample, and that becomes much more cumbersome to do when you have a complex model with multiple sources of variance, which we will shortly have. So in this case, I would have created a new variable for x1 that I'm calling x1c by subtracting, say, 10 off of it. I decided on 10 for this one. I decided on 5 for that one. And my statements then would look like this. Here's my contrast for whether or not those two predictors give me a significant R square. I've changed the name of the variables, but I've otherwise left the code alone. So true or false, is my R square going to change after I center my variables? No, it better not, or I did something wrong. This is an interpretation choice. It's not a goodness of model choice. These estimate statements then show you examples of how to ask for predicted outcomes for particular levels of your covariates. By the way, I say predictor and covariate interchangeably. Those words mean the same thing. X's broadly construed. Another way to think about this is that I'm asking for different intercepts than the one the model is for. So in the output that comes up after I put solution, what I will get is an intercept that describes my expected Y for what kind of person. Is the conditional mean of Y for somebody with what characteristics? Not a trick, I swear. No tricks, no trickery. I will warn you if I'm tricking you. You're smiling at me. That means you know.
Are you talking about the first line, like when x1 is 10, x2 is 5?
I'm just saying, what
saying
does the
in
intercept mean, given the centering of these variables? It's predicted Y for what kind of person? Average, more specific than that though. Somebody with? So this is what I'm talking about. What does beta 0 mean? Expected Y when what is true? When these are 0 in the centered variables, which translates into what in the original variables? Is when somebody has a 10 on x1 and when somebody has a 5 on x2, that's when these terms zero out, and that's what the intercept means. That's all I'm looking for. So that's what beta 0 means. So by default, the model is going to give you the predicted value for one kind of person, a conditional mean for somebody who has an x1 of 10 and an x2 of 5. Now, if I wanted to make a picture or generate predicted values for other kinds of people, what I'm actually asking for are predicted intercepts. Predicted intercept, predicted outcome, predicted conditional mean, all those words mean the same thing. This is how you do it. So I'm labeling these things so that you can see the pattern. How do I create a predicted value? Well, if I go into my equation here, it's kind of like I'm ordering at the drive-thru. It's like, thank you to Renza, how can I help you? And yes, it is going to be Renza in my example because I'm from Nebraska. And you guys may think Renza is gross because Kansas people do not understand it. But back in Lincoln, there was like one Renza every 10 blocks, and it wasn't enough because they were always packed. So yes, welcome to Renza. Would you like to supersize your order today? No, thank you. I need 1 beta 0, and that's it. Okay, your order total is $4.55. Please pull around. That's what this first line of code here does. I need 1 beta 0, and if I am requesting an order for somebody who has x1 10 and x2 5, I don't need to put in any values because they are 0 for that kind of person. Next line down, what if I want the predicted outcome / conditional mean / predicted intercept for somebody who has an x1 of 8 instead, and an x2 of 4. I still need a beta 0 for that person because that's my you are here sign. From there, I've got to go up or down based on the values of the covariates. These covariates are both lower than the centered values, so I go down by 2 for this coefficient for beta 1, and I go down by 1 for this coefficient for x2. So the values that show up here after these variables are the multiplier of how many beta 1s you need based on your value of the centered x variable, and how many beta 2s you need based on your value of the centered x2 variable. So this model has one slope for beta 1, one slope for beta 2, and those things can create an intercept for any combination of the predictors in the model. So these estimate statements can be used to get ones besides the default for your reference person right here. How are we doing? I see some people going, So tell me what that looks like. Are you thinking, why do I need this in my life? Are you thinking, why does this sound strange and unfamiliar if she's talking about regression? Are you thinking, I know how to do this, move on? See, those are very different thoughts, but they all kind of have the same look behind them. What do you think, Teresa?
I'm thinking of homework too.
That's a good way to think about it. Yeah, see, the good news is that I never ask you to do anything I haven't shown you some kind of template for. So yeah, I'd be asking for predicted values, and this would be one way to get them. Who else is thinking? No, no one's thinking. No one admits to thinking anyway. Everyone's afraid I'll call on them. Fair enough. So categorical predictors. Now this is where it gets tricky trying to figure out what your output means. You've got two options. Both of these are equally correct. One may be more convenient than the other depending on what's in the rest of your model. When you have a categorical predictor, meaning a grouping variable, if it is 0, 1, it's probably easier just to pretend that it's continuous most of the time. So you would have a dummy-coded variable, for instance. Like if I have gender, for instance, somebody's got to be the 0, somebody's got to be the woman, if it's a 2-category variable. Sometimes you will see contrast or effect coding at the bottom of the screen here, like a -1.1 code, or -1 + 1 coding for grouping variables. Have you seen that before? Yeah. See, I don't like this. I don't like this because where is my intercept? For what kind of person is my intercept for? You could speculate and philosophize. Is that a word? Philosophize? Philosophy? Yeah, I think that's a word. Sometimes it's not true. I can't tell when I'm up here talking. Philosophize about what it means to be a 0 in a variable that's coded like this. But generally speaking, there's no one who gave you that answer. So I don't like this because the 0 point doesn't mean anything. It doesn't make it wrong, it just makes it weird to me. So you'll rarely see me do that with very, very few exceptions. So let me show you then an example, including a gender variable that we are going to treat as continuous. And then we'll look at how to treat multiple group variables as either dummy codes or categorical codes, because this is something you'll have to do repeatedly. I don't know if it's streaming or not. We'll have to see. It says it's offline. That's not good. But maybe it's just because I haven't. No, it says I'm streaming. All right, well, I don't know. I'll figure it out later. So I have example 2 here. This comes from chapter 2. We'll do the first part of it this week, and then we'll pick up the interaction terms part in a few weeks. This is a fictitious data set, which is why I'm able to give it to you, but it's based on a real data set. So the story is I have 550 older adults. I am predicting an outcome that is a measure of cognition, so it's a measure of a crystallized intelligence information test. And I have age, which is centered at 85 years, which is near the middle of my sample. I have grip strength, which is a very common measure of physical health in older adults. So it's measured as pounds per square inch that you can squeeze, where the mean is somewhere around 9. And then I also have gender in the current model, and then eventually we're going to have dementia diagnosis, where 1 is you're not going to have it, future means at some point in this longitudinal study you will have it, and 3 means you already have it. So this is time 1 data from a longitudinal study for this example. As you learned in Making Friends with SAS, you can define an abbreviation variable that goes everywhere in the code for where you want to be able to import or output files. And so this is pointing to where these files live on my Dropbox. If you wanted to run these files on your own, the files are in a zip folder on the website, and you can do that yourself. Note that I have taken this abbreviation and used it here so that I only have to type this one time. So when it reads this, it's going to say everywhere that you see this file saved with an ampersand in front and a period in back, it is going to fill in this place. So I'm using that to define a SAS library. I'm importing my data. So what does data mean again? Make a new data set. Where's it going? Work. It's going to be called chapter 2. What does set mean?
Where are you going to take that
from? From where? What happens if I forget my set?
It'll be empty.
Yeah, make a new empty data set, because I'm not pulling data from anywhere to make a new one. So it is coming from file save, which is this place right here, and it is already a SAS data set, and so that's the name of it without the extension. I already have my gender variable coded such that men are 0 and women are 1, but I am creating 2 new predictor variables by centering them near their mean-ish values. A convention that I always use in my code is to put the centering constant at the end of the variable name so that I remember what it is. Some people would put a C or something like that. Whatever you want to do is fine. I'm just telling you that's what I do. So age 85 is age centered such that 0 refers to an 85-year-old. Grip 9 is grip strength centered at 9 pounds per square inch. And then we will deal with the rest of these variables in a little bit. I'm adding labels for good housekeeping so that I remember later on how I made these things. And then run says make it go please. Here is descriptive output for the variables, so you can see what these things look like. So I'm asking for proc means for my 2 predictors and for my cognition outcome. I'm also asking for frequencies for my group variables and correlations among them as well, which I didn't show here. So your SAS output looks like this, right? This style, by the way, is called HTML blue. There's all kinds of SAS styles that you can make it any color you want. So you can pick other colors if blue is just too plain for you. You will rarely see this in my handouts. Most of the time, the handouts that I build are going to be using the old school SAS output because this is way easier to manipulate into a handout and to annotate. The HTML tables you have to paste and then translate them into pictures, and it's just, it gets very annoying. And so you will see the output that looks old school like this, but it's the same thing. And when you run the models, the code that I gave you, you will be able to get both versions of it. All right, any questions on the setup for the exam? Okie dokie. So we're starting with an empty model. Do you remember this term from last week? Maybe? What does empty mean? No predictors. This is something that you've probably never done in a regression model and arguably don't need to, but it's the first thing we're going to do in longitudinal models. It tells us how much variance there is to be predicted. In this example, each person is only measured once. This is a cross-sectional example. So I already know how much variance there is to be predicted just by running descriptives. Here's my standard deviation right here. That squared tells me what my variance is. But in multi-level models, these empty models will be useful to carve up variation into levels. How much is specific to people, how much is specific to time, how much is specific to group, and so on. So this is our first step. So proc mixed data equals the data set. These are options that I typically include for things to print or not print. Method equals REML is the default, and that is the same as least squares, again, if you have complete data. Cognition is my outcome, so it goes right after model. And then note, after the equal sign, there's nothing before the slash. And Word is unhappy with me about this. It's empty. There's no predictors. That's where the predictors would have gone. Solution says, hey, can I have my output, please? Degrees of freedom is right here. This isn't something we'll worry about yet, but this is set to be the typical way degrees of freedom are calculated in regression and ANOVA models. Now this is something brand new. Wherever possible, I have written little programs to automate calculations for things that SAS does not do automatically that I wish it did. So this is going to be the first example of this. I am going to open up SAS, this example here, on my little machine so you can see what happens when I run that part. So this is what's posted online, excuse me. Here is SAS. Let me make this a little bigger so we can see. At the top of the program are options that are used to make the output have less crap in it than it is by default. And then you'll see these things here. Comments are in green. It says, these are macro programs to automate calculations. Nothing needs to be changed. If you want to use my little programs that are designed to do math for you, these things need to be in your file, but you don't need to do anything to them. Now, do you remember macro programs? We talked about that a little bit last week. The idea is that macro programs do things, they write SAS code for you using a metric of find and replace. So I will explain how this one works in the context of this example. So first thing that I'm doing then is running the code to import my data that we went over before. Check the log, everything is nice and happy, hooray. Run descriptive statistics. I'm going to run my empty model here. There's my HTML blue output. Now over here on my libraries, here's the work library. I have two little files. Here is the chapter 2 data set. Here is a new data set called Cove Empty. So what that line of code does, ODS output means save this piece of output as a data set, a SAS data set. If you don't tell it where it goes to work automatically. This little piece of output right here that says covariance parameter estimate, that thing is called coparms to SAS. So what I'm saying is take this chunk of output called coparms and save it as a data set called Cove Empty. That's a name I made up. Cove because it's a covariance parameter data set, empty because it's from an empty model. So when I run this chunk of code, not only do I get the usual output here that is on your sheet, but I also get that little table saved as a data set. I am then going to use that table, add to it a table that has predictors in it, and then I can use that information to calculate R-squared for you. R-squared does not show up by default in proc mixed because there is no regular formula that would hold for all cases for it. So this is a workaround that I've developed for you. So it tells you how many cases it read and how many it used. This is important to keep track of. And then you get this thing, Cove-Parm residual. Can you guess what that is? Give me synonyms for the word residual. Error, right? And it's one number, so it can't be the error for a particular person. What is it? For everybody. So this is error variance. This is residual variance, mean square error, and what it would be called on your regression output. It gives you an estimate for how much error there is and a standard error around it. It also gives you a Wald test. However, you are never, ever, 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 ever allowed to use these numbers. Got that? You can't use Wald test for variances because variances don't have two sides. What's the smallest number that a variance can ever be? 0. The whole idea of a Wald test is that you should be able to go 2 standard errors on one side and 2 standard errors on the other. But if you have a variance that's estimated as a very small number, it hits the wall of what it can be on one side. The sampling distribution is not normal. So those Wald tests are not valid for variances. I will teach you another way to decide if a variance is significant instead. Fit statistics are given to you here. These are going to be relative fit statistics. We don't need to worry about these yet. They are going to be used to decide about the variance side of the model, and right now we're focused on the fixed effects. Solution for fixed effects down here. This is your model for the means. So right now all we have in it is a single intercept, beta 0. If I know nothing else about a person, what's my best guess for their outcome? The mean, right? There it is, 24. Not coincidentally, the mean is 24 if I just run means. And if I square this 10.99 standard deviation, guess what it becomes? 120. So this model is the definition of variance, how far off each observation is from the mean squared. So this 120 is as bad as it gets. This is all of the variance that there is to be explained in cognition. Now we have a jumping off point to see how well we can do by putting in other predictors. Here's a model that adds in 3 predictors. These titles, by the way, you can put whatever you want here. They will show up on your output to help you scroll through and find things. So I have added age centered at 85, grip strength centered at 9, and my label here for sex MW means men are first and then women are second. So men are the 0, women are the 1. I have added a contrast statement to give me the R-square significance test for adding those 3 predictors. So I've listed each variable with a 1 after it separated by a comma so that I know that I have a model that has 3 terms in it used to calculate that F-test. I have also added this chi-square option so that it calculates chi-square instead of F as well, so that you can report either one. So my residual now, it was 120 before, it's down to 109. That's better, right? We've gotten a little bit of the variance explained. How much? Yeah, you're like, sum. There's a formula for how much it is. You'll see this over and over again. But quite simply, it is was minus is over was. That's your R square. In this case, it was 120. It's 109 now, and it was 120. If I pull up an Excel, equals 120 minus 109 over 120, 9%-ish. That's my R square. So of the 120 I started with, it went down by 9%. Now, do I want to have to pull out Excel and do that for every single model that I run? No, that's annoying. So that's why I made you a little macro program to do this for you. In this SAS program here, I asked it to save the covariance parameter data set as a new table called cov age grip sex. There it is. Then this statement below here calls my program to calculate the R square for you. It takes 3 pieces of information. It allows you to do R square and change in R square. Given that we don't need change in R square yet, I put the empty data set in both of these places. And the data set that has the most stuff in it is the one that we just had. So once you have ran this program in memory, I just hit F3. You put in the names of the data sets here that has either fewer parameters or more. Run that little piece of code. And then your output spits out this table. That gives you the R square. So could you do this in Excel on your own? Absolutely. Do you need my program? No. But this is designed to make your life easier. I don't like typing things when I don't have to. This is what you're used to showing up by default when you run a regression model or an ANOVA model. It does not show up by default in mixed, because as you will see, there's lots and lots of different ways to do R square in models that have multiple variance components. So that's what these ODS output statements are doing for you. They're saving pieces of output so that you can make the program do math on them for you. So here is my model. I have added out to the side here some annotation. This is not included by default. This is what I would call prompt Lesa, trying to be nice to you. I'll tell you how to map the terms back into the model. So my intercept is now 26. For what kind of person is my expected cognition outcome 26? What's my you are here sign? Where am I?
Age 85, grip strength 9.
Age 85, grip strength 9, and dudes, yes, when sex equals 0. That person gets a 26. What does my model say happens if I am 86 instead of 85? We'll turn this into a two alternative forced choice. Does cognition go up or down if I am older? Down significantly or non-significantly? Right. Estimate, standard error. Estimate over standard error gives you that T. Here's the p-value that goes with it. Survey says significantly according to an 05 criterion, or maybe even an 01. By how much a year does my cognition go down? 0.4-ish. Yes. Now, is that true for both men and women? Does it matter if I'm an 86-year-old woman or an 86-year-old man? Does it matter? Does the effective age matter? Is the effective age the same for men and women according to my model? I don't know, but according to my model, it is. Each of these effects are specified as additive main effects. They're not interactive. So my intercept is conditional on all three being 0. This effective age is for everyone. No matter who you are, for every year older, 0.4 down. Or for every year younger, 0.4 up. Whichever way you want to think about it. Likewise, main effective grip is 0.5. What does that mean? What's increasing? Not my grip strength. Cognition. Yeah, is that what you said? I'm sorry, I didn't hear you correctly. Yes. So for every, think about the story here. What's a unit in the story? Pound per square inch stronger. My cognition is predicted to be higher by 0.5. So stronger people are smarter. Yes, I shouldn't have skipped the gym today, huh? And then last but not least, men are the 0, women are the 1. Who's doing better in my sample, men or women? Oh, it's forced choice alternative, 2 forced choice. Men are the 0, women are the 1. Who is doing better? The men are better in this case, because the women are the 1, they get the -3 on their score. The men have a higher cognition by 0.3738 significantly in this case. Is that, I'm going to make up a word, is that irregardless of age? Yes, according to my model it is. According to the model. Say what?
Can you say that additive part again?
Yes, these 3 terms are additive. They're not interactive or multiplicative. That means that each of them gives an increment to the score equally across the entire sample. They are fixed effects. So the age coefficient applies to all levels of grip strength in men and women. The grip strength coefficient applies to all levels of age and to men and women. The gender difference applies to all levels of age and all levels of grip. In this model. Question?
Does that mean these 3 predictors are not correlated at all?
No, they are correlated, in fact. Each of these coefficients represents its unique effect controlling for the other variables in the model. That part hasn't changed. That will always be the case. But in terms of predicting who an effect is for, right now each slope is for everybody. Unconditional. The only way it's not for everybody is if a slope is part of an interaction term. So each of these predictors is significant in this case. How do I know if the variance that they accounted for, that 9% that we found, how do I know if that is different than 0? Normally you would get your F-test for your R-square, right? I asked for it via contrast, and that shows up right here. So yes, you can report it as a chi-square or you can report it as an F. F times degrees of freedom equals chi-square. 6 of one, half dozen of the other. The fact that it's significant means, yes, that 9% of the variance that these three together accounted for is significantly greater than 0. And here's the output that's created by the R-square program. And here's the math that goes with it. What it was minus what it is over what it was. What was the variance before adding in these predictors? What is it now over what it was? Gives us the percent reduction. Okay. So in terms of reviewing vocabulary, what is this R-square F-test thing called more generally? That's a multivariate wall test. Yes. What are these significance tests called? Univariate wall test. And some people will correct you and say that a wall test has to be a Z instead of a T. You could call it a modified univariate wall test because it uses degrees of freedom. But those are the concepts that are going to show up again in the world of longitudinal multi-level modeling. All right. Any questions on any of this so far? Not yet? Alright. Then let me look at grouping variables as a special case here, because this is very easy to get confused. So you've got two options for grouping variables. Either you create codes for them, or you let the program do it. Either can be correct. One may be easier in certain circumstances. So let me show you the hard way, the longer way, which is more useful sometimes, of you creating contrast for a grouping variable. So for instance here, if I have a 4-group variable, let's say that I have a control group and 3 flavors of treatment. If I use this treatment group variable, it's coded 1, 2, 3, 4. I can't put that in the model because I can't put a slope through it and say that a unit difference means the same thing across all levels of the variable. I lost my remote thing here. Nah. Over there? Yeah, I wander around and I lose things. This is the problem. So here is option number 1 for how to model treatment group. Since it's 4 groups, I need 3 new variables. And I have coded these as D for dummy, D1, D2, D3. The intercept is the group that always gets a 0 across the 3 variables. So that is going to be who? Who is my intercept? Which one always gets a 0? Control. Yeah, D1 is going to represent the difference between control and treatment 1. D2 gives you control versus treatment 2, and D3 gives you control versus treatment 3. However, those interpretations are only going to hold if all 3 of the contrasts are in the model simultaneously. For instance, if I screwed up and I did this, outcome equals D1 all by itself. If you look at what the codes mean up there, that's actually going to give me the contrast between 0 and 1, where 0 is the average of control treatment 2 and treatment 3 versus treatment 1. If that's not what I wanted, then I screwed up. So all 3 variables have to be in the model for those contrast interpretations to hold. The fact that this 4-group variable takes 3 contrasts to represent all possible differences indicates then that to get a full test of group, that requires a multivariate wall test that has 3 degrees of freedom. Once you have that 3 degree of freedom test, the model will actually tell you any of the group differences. So in this case, how many possible group differences are there among my 4 groups? and do it, work it out on your hands if you want to. That's how I do it. I've got these three, right? I've also got T1 versus 2 and 3, and T2 versus 3, right? There's got to be 6 altogether. Now what about on the output? Which of those 6 differences is going to be showing up for me? Only those ones. What if I want to know if treatment 2 is better than treatment 3? What are my options? Hope? Pray? Guess? Speculate? I could change the reference group to make it treatment 2 so that I could get all its comparisons. And I could keep doing that as many times as it takes, right? The model already tells you what it is. You just have to know how to ask for it. So this is where what we're going to do next time then. If the model tells you what the predicted mean is for each group. So for control, it's the intercept. For treatment 1, it's the intercept plus the difference for treatment 1. And likewise for the others. Then the model has to tell us what the differences are between the non-reference treatments. And it looks like that. For any group, regardless of whether it is the reference group, the model will tell you what its mean is, and therefore it can tell you what the mean differences are between any of the groups, regardless of who the reference is. You just have to know how to ask for these latter ones because they're linear combinations of beta weights. Beta 2 minus beta 1 is how you get T1 versus T2, 3 versus 1, and 3 versus 2. How you ask SAS or any other program to linearly combine beta weights to add them or subtract them is via our friend estimate statements. So that's what we'll go over next time. How to get all of the pieces of information that you would ever want out of one model. Ta-da! Trust me, you're going to love it. It takes a little getting used to, but you're going to love it. So we are out of time then, just as I was getting all ready to go here. This class is just too short. Said no one ever. Let me know if you need help with your homework for SAS. Otherwise, I shall see you on Monday. Office hours start now.